All right, so this is a talk about engaging the HEP community in Julia, because quite a bit of it is non-quantitative, kind of subjective talk. I'd like to start with something objective. Let's start with some numbers. So at last Friday, just a couple of days ago, I refreshed analysis of what programming languages are particle physicists using. And I got it all onto one slide, so that makes it a complicated slide. So we can take a minute or two to digest what's going on here. I've been trying to improve the technique a bit by not seeding on CMS, even though it's very convenient that there's CMSSW that lets you identify all the who would fork CMSSW other than a CMS collaboration member, but quite a few of some 10% of them fill out their GitHub bios, and of those, some 20% write something like particle physicist or high energy physicist. So we try to get a more unbiased sample, sort of more, what is the whole community like? What is the whole field like? We can try selecting GitHub users by them saying that they are particle physicists, basically. Sometimes they're saying they're former particle physicists, or some of them are theorists, some of them are professors, a lot of them are students. And then when finding these, still, Google's being annoying and telling me that there are 4 times as many matches as men. It's allowed me to see, but okay. But anyway, this is at least selecting sort of an unbiased set. If there's any kind of bias, the what Google is showing me is probably the more active users. These users got about 275 of them. Have on average 15 non-fork repos, so they're pretty active people. So maybe it's biased toward more active people. But okay, so accepting that, then we can look in all of their non-fork repos, and by listing files and looking at what file suffixes there are. How many people are using, how many of these people are using at least one Python file? Well, quite a lot of them. How many using Shell or C? Quite a lot of them. Here's a surprise. Web like HTML or JavaScript, that's also quite high. That's something I didn't know before doing this study, because this was first get the users, then look at the file extensions, and then ask, what are these files? Something that was unsurprising is the amount of LaTeX. There's quite a bit of LaTeX in these repos. And then probably because of the theorists, a lot of Mathematica. And we're coming down to Fortran, various spreadsheets, and now into just, the potpourri of, other languages. And in this scale, about 5% of the people who identify as particle physicists, maybe the more active ones, have written at least one .jl file. Which is something, although it is sort of out here. We would describe this as like not adopted yet. But next page, you saw Julia was right next to Rust and Lua on that previous page. But if you look through, like, instead of what files are people making in GitHub, what are people talking about? I went to Indico search, and for all of the materials, the minutes, the slides, a couple of papers, but mostly meetings in the past year and a half, there were more talks about the Julia programming language than other programming languages, like compared to Rust or Lua. And then also filtering out, not including people named Julia or Rust of the oxidized metal. it's still what we see if we're looking at what people are talking about. They're talking about Julia more than any other, like let me call it third-party language, not C++ and not Python. And also the ones who were talking about Rust, those same documents were referring to Julia. So they were really just talking about other languages, and Julia and Rust are the two that come to mind. At ACAT and CHEP, the most recent one, there were quite a few talks at the last CHEP, 3 talks about Julia, and they were specifically about Julia. Contrast to Python, there are not so many talks specifically about Python, but it comes up in a lot of the abstracts because it's sort of deeply sort of rooted in the soil. And the only other programming languages mentioned were C++ and Java. There was no like Rust or Lua or anything like that, Swift, anything. And also, it's the only language-based HSF other than PyHEP. So like what I'm describing here is there might not be a lot of use yet, but there's a lot of momentum. So Julia is not adopted in HEP in a general, across the board kind of way, but is getting more attention than any other rival to C++ and Python. So from here, it could continue to rise in prominence, or it could end up passing as a fad. This is a critical time. This is like a junction point. As we've seen, Julia is a perfect fit for HEP technologically. It allows for, and this is what I like best about it, it allows for an exploratory phase in which the data analyst focuses on what to compute, like, computing the Julia set, not worrying about types, just, what's the algorithm? And so you can, write the code that gets you the answer without worrying about how it's accelerated. And then this exploratory code can be tweaked in gradual ways to scale up to large data sets, to get faster. And the thing that I like most about this is that this is a gradual path from brainstorming to optimized code. It is not a rewrite. And that's always a good thing when you can get something that there's a clear path from here to there. It's not start over. However, this argument that's focusing on Julia as a solution to the two-language problem, it's hard to see how we can get there by some gradual path. It's hard to see how we can get from our current 2 languages to a 1-language world without going through 3. Because right now, when we've got the 2 languages, C++ and Python, in order to get to some, future utopia where everything is Julia, and so therefore it's expressive, it's convenient and fast. To get there, you have to start getting people to start using it, and it's not like the old stuff is going to go away in the interim. In the interim, there will be 3. So preparing a complete stack of HEP tools in Julia will help adoption, but it's not going to eliminate the interim 3-language period. Just the fact that there are Julia tools for doing a particular thing doesn't mean that the C++ and the Python tools go away immediately. So if you build it, doesn't mean that they will immediately come. There will not be any clean break in which everyone is ready to set aside their old tools and take up the new ones. That'll have to happen, slowly. And the closest approximation in history to that in HEP was the Fortran to C++ transition, which was mandated top-down. You'd often be like a new experimental collaboration will start, and they'll say, okay, we're going to be all C++. And that was this kind of clean break that actually lost a generation of HEP programmers. A lot of people took their Fortran expertise and didn't migrate to C++. So because the general feeling is that wasn't a good thing, it won't be repeated. And also, if we're focusing on the data analysis step, that's not top-down anyway. People can use whatever tools they want to in order to produce the final paper. So we need to give users short-term reasons to add Julia as a second or third language to their analysis work, if they're already using one or two languages. You'll be able to replace all your Python and C++ as a long-term reason. It's not going to explain why they should start doing it, why they should add it when they've got deadlines and et cetera, et cetera. So what we're trying to do for this in the awkward array group is adding Julia to the mix. So here we have the awkward array repo. Awkward array.jl is a semi-separate project. It's at least a separate repo, much newer, and it's 100% Julia. This is what I was proposing at our last mini workshop. I was saying that an awkward array Julia bridge could help to introduce HEP people to Julia. And it's being presented in awkward array as another JIT compiled backend. It's one of a few of these JIT compiled backends, so they're already recognized as being good, useful things. But you'll see, I'll show in a moment that the Julia one is going to go farther. So in Numba, awkward arrays can be arguments or return values of Numba JIT compiled functions. This is also true in Numba CUDA when you're running on GPUs. You can send awkward arrays to a GPU. Into root our data frame, there is a C++ JIT, which is modeled very closely on the Numba JIT for awkward array. And this is what's used to get awkward arrays into our data frame or data from our data frame into awkward arrays. And then also this same C++ JIT compiling bridge can be used with CPPYY by itself, so that you can use it the same way that you would use Numba. You can define a C++ function with CPPDef and use awkward arrays as the arguments and return types. And now we have Julia as well. But this is not like the other ones. In Numba and C++, we define a Python lookup object. This serves two purposes. One is to hold a reference to the awkward array, preventing it from going out of scope, so that it will remain in scope and remain in memory through the duration of the compiled function. And then another thing that this lookup does is it presents the tree navigation data in a raw byte format, so that this compiled thing can work on it. Then the Numba or C++ array view object points to a position in the structure. It's really just a cursor. Where am I right now? So that they're very lightweight and it can run around. And then they're also JIT compiled differently for each tree node type. But the point about all that is that Numba and C++ do not own the array. It's a borrowed reference. But in Julia, we define the whole layout tree with native Julia structures and convert. So Julia can own the array. Topologically, this means that if you're using the Numba or C++ backend in awkward array, you can send the data into the compiled language and do some compiled things on it, but the control has to return back to Python. That's just how it's designed. Whereas the Julia one is designed differently, so that you can do a one-way copy or view to Julia. And if it's a view, I'm not really sure how the reference counting is going to work with that. That's actually one of the open questions. But you can do a one-way copy or view into Julia, or you can do a one-way copy or view out of Julia. There are rationales for why we designed it this way in Numba C++. I'm going to just skip over this. This is, why did we do this? It wasn't for bad reasons. And why did we do that in Numba and C++? It wasn't for bad reasons. But also, so this opens the door to unroot becoming a drop-in replacement for uproot in Python workflows. That's part of what we had in mind, that we wouldn't be using Julia just for function acceleration the way that we are with Numba and C++. We could, get new arrays from Julia. or send it to Julia and never look back. That sort of thing. This was discussed at PyHEP Dev. There's always this sort of back burner. Well, what about having an uproot in C++, so that the problem of opening a file is not so time consuming. So because uproot is in Python, once you've found and decompressed the array data, then that's quick. But getting to the point where you know where the T basket is involves a lot of Python steps, and that is slow. And a compiled language can do that faster. And so among the things that we talked about, and actually the one that we, if you follow this thread further, the one that we narrowed in on was if we want a compiled uproot, let's just use unroot. I mean, we have to cross languages anyway. Let's use Julia. So there are a few technical benefits of awkward array JL over Python. By re-implementing awkward array in Julia, there were some advantages over implementing it in the first place in Python. One is this composability. All of the buffers in an awkward array content tree are abstract vectors, so you haven't tried it yet, be able to swap into special features like GPU resident arrays, autodiff units, and that sort of thing. Whereas in Python, our NP-like backends are complicated by the fact that we have to use array-oriented functions. And that's a larger API. We are using dozens of functions from NumPy. They will differ in some of the details when you go into CuPy, that it's not 100% drop-in replacement for NumPy. And especially something like JAX is quite different. So each new backend needs a shim. Whereas the abstract vector, the API is just iterating or finding an element, because imperative is fine for performance. Unification, this was kind of a surprise getting into it, that since push and append are implemented on abstract vector, and the awkward array is an abstract, and it is an abstract vector, our functionality of layout builder, which is an append-only array in normal awkward, and awk array, which is the read-only array, are now unified into the same object. And there are reasons why they have to be separate in Python, well, coming down to the two-language problem, but in Julia that unifies. That's neat. Some examples of awkward array.julia. So here's one where we create an array with a given type. So we now know how to push and append into it, what kinds of things can be pushed and appended into it. And then, so this is the layout builder functionality. And here's the awk array functionality. You can iterate over this thing and, or get it by element and that sort of thing. Two vector from iter, kind of standard things. And we want to also have on the Julia side, to arrow from arrow, so we can communicate with all of the Julia tools that use arrow. A big deal, and you should see Janus talk later in this workshop, is we definitely want to round trip data between Python and Julia. That's kind of the reason for being for this library. Jerry has already added a tables interface, which is great. So yeah, and we are aware of array of arrays and vector of arrays. What we're trying to do here is model the awkward array, the whole thing with. So we know that, like, for example, this example could be done with vector of arrays. So don't miss Jana's talk, and also find Jana if you can, because we have some open questions about how to glue the Python with the Julia. That's sort of the next step in this process. So yeah, that's our open question. In particular, if I could focus in on it, like, how does package management work in a Python plus Julia environment? Like, we want to respect both languages, favorite package managers, and I think it would be fine if the Python side is required to use conda and can't use pip. I think that would be okay because of the binary dependencies, like the Julia language itself. But this PyCal and PyJulia, they cross the language barrier, and so they have dependencies in both languages. Is there a way that we could use Conda for the binary and Python dependencies, and then Julia's built-in package manager for the Julia dependencies? Yeah, this is an open question. We want to know how to. We want to not just get this to work. We want to know how to do this right. So conclusions. We need stronger connections between the HEP analysis tools in Python and the HEP analysis tools in Julia. I should have written that for Python and C++. I could see that there are a lot of these HEP tools coming up in Julia, and that's great, but we want this to not become a silo. We want it to not be something where, in order to use the tools in this ecosystem, you have to buy into the whole ecosystem. We really want, if we're going to get these on the fence HEP users in order to start using Julia, they're going to need to be able to use it with their existing tools. So we want to keep that in mind when developing new tools. So yeah, I should open to questions.